Hello and welcome to the lecture Visual SLAM. In this lecture, we are going to discuss the different aspect of SLAM. First, we start with define the SLAM. Then we define Visual SLAM. Then we try to understand what is the objective of the Visual SLAM architecture and different categorization of Visual SLAM. Then we understand what is the evolution of Visual SLAM, ORB-SLAM, and we conclude different deep learning based Visual SLAM models. The simultaneous localization and mapping is a very interesting computer vision problem where we do mainly two things. One is localization and one is mapping. And these two is being done simultaneously. So basically, if we go a bit technical way of explaining, it is estimating the pose, and based on this pose, we do build the environment map or surrounding map. So by definition, this SLAM or simultaneous localization mapping refers to a problem of enabling a robot to estimate its own position. Okay, that is very important, while simultaneously building a map of its surrounding environments. And that is very important, that basically estimate its own position and building a map, or we can say bit in another sense, the first generate a map of the surrounding and try to find its own position in this map, and vice versa. Okay, so these two processes are inherently interdependent, so that we understand very. Just for example, for a human being, when we walking through roads, this is automatically done in our brain, that we not only find our own position, we find our position in the surrounding locality or surrounding the maps. So this is basically done in this simultaneous localization of, that means we find our position in a particular area, and this area is framed in our brain at the same time. So this is just an analogy, and we can now understand these two processes are inherently interdependent. It is accurate localization requires reliable map, while consistent mapping depends on knowing the robot's position. So those two things are very much interconnected. This mutual dependency makes SLAM a tightly coupled and complex estimation problem. So as a whole, it's a estimation problem, right? The two basic agenda, and these agendas, pose estimation and environmental map building, that is very tightly coupled, means it's very much interconnected. So as a result, it is typically addressed using probabilistic method and optimization based techniques to handle uncertainty and ensure consistency. Since that's the basic idea of SLAM. Okay. Now, SLAM is the computational problem that we understand of constructing or updating a map of an unknown environment while simultaneously keeping track of an agent location within it. So that what we have said, that we constructing and updating a map. Why constructing and updating? Just for example, a robot is walking. When somebody is walking or something is walking or in motion, definitely the surrounding environment is keep on changing. So we are constructing that new environment or updating the map for an unknown environment. But because a priori you don't know, when we are walking, our surrounding environment is changing. So we consistently constructing and updating a map of our environment while simultaneously keeping track of its agent location. That means this robot location within this map. So this problem is basically address the problem of robot autonomous navigation in an unknown GPS denial environment. So SLAM is very much helpful when GPS is not working. For example, underwater or exploration. So what is the objective? The objective is to compute the robot's pose and the map of the environment at the same time. So that is basically the main objective of SLAM. That's why it's called simultaneous localization. Okay. Now come the visual SLAM. What is the topic of this lecture? Now visual SLAM is basically a SLAM where the input are basically the camera images. So SLAM based robots or agents are mainly fitted with a singular group of sensors, normal SLAM. So visual SLAM are those systems that use cameras as the only instrument to capture information on the surrounding environment. Normal SLAM may be a group of different sensors, but visual SLAM as an input module, they use only cameras. That's why it's a visual. This is a very overall diagram that this is the image sequence. Then the feature is being extracted. Then there is something that will come in detail. That this is a kind of a front end kind of thing. This is called, sometimes loosely said, it is very one thing that is already existing, the visual odometry. Front end is very similar to the visual odometry. That feature matching, outlier rejection, optical flow estimation, pose estimation kind of thing. And analyze back end, the local mapping, inconsistent local map, local optimization, aligned local maps, and blue pulsar detection, global optimization, and so on. These are done in the back. Then we get these global pose and maps. So this is the entire system. We try to understand one by one that how actual this visual SLAM is working. Now what is the basic application of that? This is applicable to the unknown environment mainly in GPS denied or GPS degraded challenging atmosphere like indoor application, underwater applications. So autonomous navigation in dynamic environment, that underwater navigation kind of exploitation of extraterrestrial environment like Moon, Mars. So in this environment where the normal GPS is not going to work or very much weak, and this SLAM is very much helpful. Now, what is the objective of visual SLAM? Now, we see what we have and what we want to do. Now, we have the robot's control, that these parameters or these control parameters that controls the robot. So it's a sequence of control commands. For example, U1, U2, U3. So this 1, today. It tells about commands to the robot. For example, drive 1 meter forward. Okay, and there is some observation parameter, that is Z1, Z2 to Z capital T. It may be laser scan camera image. For our visual SLAM, it's camera image. So given these inputs, or we have this, what do we want? We want a map. The map to estimate a map of the environment. And another thing, what we want? The path of robot. That this path, which path the robot should go, and robot should move. So given this, we try to find out that what is exactly that these data, this observation control map, are basically not free for error. So the approach is basically stochastic. That means we use the probability. And definitely there will be uncertainties, robot motion and observation. So we use probability theory to expressly represent uncertainty. Now here you can say, we cannot say robot is exactly here. Rather, robot is somewhere here. So we use this equation, that this path and map we want given observation and controls, and that distribution we try to do. So ultimately we estimate the path of the robot and what the environment look like. So what we can specify is as a probability distribution of the path at the pose of the robot at the discrete point of time, and map given to the observation and the control. So this is the from stochastic or mathematical formulation, a very naive, very simplistic formulation of this SLAM problem. Now, SLAM is basically three main submodules. SLAM has three main sub. One is localization. It is the orientation and whereabouts of the robots in an unknown environment. That is called localization. Then mapping. It is the representation of the surrounding environment using only the relative observation of the surroundings. That is mapping. And path planning. It is the finding of the optimal route in the map, remembering the previously visited places in the map. That one thing we will see later, that robot should not move in a circular path. But let's say there is some loop or something. So it is, if it should not just walk in this loop, it cannot out of this loop. It is called loop closure. Okay, so that we'll see later. So basically SLAM has a three main parts: localization, mapping, and path planning. Now we have to try to understand what is the architecture of SLAM. Now very simplistically. So it has major two modules. One is front end, one is back end. So front end is module responsible for dealing with incoming sensor data and extract intermediate representation. That for your visual SLAM, for our visual SLAM, what we have camera images. We basically access this data acquisition and pre-processing. Front end is also commonly known as visual odometry. This sometimes is called visual odometry. This is slightly different, but it approximates visual sensor movement between adjacent images and outputs a local map. This local map provides initial values of the backend application. Where in the backend, which is also called the SLAM kernel, is usually the module that uses all the extracted information from the front end in order to construct, expand, and further correct the robot's trajectory and map. And backend does the important tasks like loop closure, bundle adjustment. We'll see one by one that what are the responsibility of front end and what is the back end. As a whole, this is the architecture. This is camera sensor data. It is coming front end, then front end output come back end, and they reconstruct the maps. And there is a loop closer is there that it basically take this data and find that robot should not move through just loop only. It should be out of the loop. So loop closer can be called the capability of robot to recognize a previously seen place and applying corrections to the graph accordingly. Another is called boundary adjustment. Boundary adjustment is a nonlinear optimization method whose goal is to rectify the both map and the camera poses by minimizing the sum of reprojection error across the multiple views. This is also simpler visual odometry with global map optimization. So we can sum up. So then we see one by one what are the different modules of this architecture. Now first we understand what the basic difference between visual odometry. It's more or less similar, but there is some difference. Visual odometry focuses on incrementally estimating the change in position and orientation of a camera by analyzing consecutive images, typically using feature detection, matching, and geometric. However, this visual odometry accumulates drift over time because it does not maintain a global map. In contrast, Visual SLAM extends this idea by simultaneously building a map the environment while localizing the camera with it. So this is a bit kind of advanced in that sense. Visual SLAM incorporates additional processes such as loop closure detection, global optimization to reduce the drift and maintain consistency over long trajectories. As a result, while VO is suitable for short-term motion estimation, Visual SLAM provides a more robust long-term solution for navigation in unknown environments, commonly used in autonomous vehicles, drones, and augmented reality systems. Now, what is the basic architecture of Visual SLAM? That, as we have seen this figure before, that is two main things. One is the front end and one is over the back end. So image sequence is there, the feature is being extracted. Sometimes feature is basically coming to this previously visited places database for this loop closure, and before that coming to backend, there is a feature matching, then outlier rejection and optical flow estimation done in the backend, and that is a relative pose estimation, and sometimes the depth estimation is also done before this. So it is more or less this input is coming here for local optimization. This first local mapping and inconsistent local maps detected and local optimization. Then this is aligned local maps, and after that, when using this loop closure, that we get the global optimization, and we get the global map and global pose. So this is the from a kind of superficial block diagram level view of architecture. Now first we understand what is the front end of the Visual SLAM. The front end is responsible for processing incoming sensor data, usually images, to extract the meaningful information of the motion estimation and mapping. That what we have seen, that from incoming data do this kind of processing on the images or the videos. It acts as a data acquisition and pre-processing step before optimizing the backend. So the front end is end. This front end in front end typically begins with a feature detection, where distinctive points in the corners and edges are identified in each frame using the methods like ORB, SLAM, FAST. So these are the image processing steps. So these features are then described and matched across consecutive frames to establish the correspondence. Once correspondences are found, the system performs motion estimation using geometric models such as epipolar geometry or essential matrix to compute the relative camera pose. So this is the front end. In some systems that use the direct methods are used, which rely on pixel intensity difference rather than the discrete features, where the front end also includes outlier rejection signals to remove the incorrect matches to improve robustness. These are all basically doing this feature engineering. Another key component is keyframe selection. That all frames are not very important. Some frames selected, where only certain frames are chosen for further processing to reduce computational load while preserving important structural information. In this RGB-D means with the depth map also. The stereo RGB-D setups, the front end may also perform the depth estimation to recover the 3D structure. Overall, the visual-SLAM front end provides accurate real-time tracking and feature information that feeds to the back end for global optimization and map. So that is the basic idea of front end. Now here is the one important thing is called pose estimation. Pose estimation is the process of determining the position and orientation of the pose, that means the pose of an object of the camera in space, typically using sensor data such as images, depth maps or inertial. In computer vision, pose estimation often involves detecting the keyframes in the image that we have said. Is keyframe identification, matching them across the frames to infer how the camera object has moved. So these are the basic idea of pose estimation. It is the fundamental component in application like robotics, augmented reality, autonomous navigation, where understanding spatial relation is critical. Now, visual-SLAM builds upon this pose estimation by not only estimating the camera's pose over time, but also construct a map of the surrounding environment. So even the camera's pose, that means robot's pose, that is very important. It is not estimating the somewhere else pose. The camera is in robot and it's robot's pose. Using the sequence of images and sometimes additional sensor, visual-SLAM systems track features, estimate motion between frames, incrementally generate the consistent map. That is a part of it. This allows devices such as robot, drones, these AR systems, augmented reality system to navigate unknown environment in the real time while continuously refining both their location and values required. So this is somewhat the pose estimation. Now we'll find out what is the input and what is the output from the front end. The front end takes raw sensor data, converts into the structured information that can be optimized by the backend. So what are the inputs? Image data, monocular, stereo, RGB-D, whatever. In camera frame, sequential images. Camera calibration parameters, the intrinsic parameters, the focal length, distortion, and sometimes in the extrinsic parameters also. So optical sensor data from IMU, the visual inertial SLAM, depth sensor or stereo disparity. These are the input to the front end. Now what is the output? Is feature information, the detected key points and their descriptor. Feature correspondence, the match between the features across the frames. Estimated camera pose, the local motion. Relative transformation, rotation and translation between consecutive frames. Keyframe estimation, estimate the keyframe. Selected frames are representing important viewpoints. 3D landmarks, the initial estimates that triangulated points in space, especially in stereo RGB-D system. And tracking status, the information about whether the tracking is successful or not. So these are the basic outputs that is fed into the back end. So this is the basic idea of front end, what it take the input and what it produce. Now come to the back end of the visual-SLAM. The back end is basically responsible for defining the camera trajectory and the map to ensure global consistency accuracy. That is the main feature. While the front end provides initial pose estimates and feature correspondence, the back end performs the optimization and minimize accumulated errors drift. That is basically it. The central component is pose graph optimization, where camera poses are represented as the nodes and the spatial constraint between them as edge. Optimization technique adjusts these pose to best satisfy all constraints. Is it them? Another key is partner adjustment. while jointly optimized camera poses and a 3D landmark position, minimizing the reprojection error across the multiple frames. That is called bundle adjustment. And this significantly improves the accuracy, but computational expense, so it is often applied selectively, mainly on the keyframes. The backend also handles the loop closure detection correction. What do we mean by loop closure? If we can see, a robot is basically moving in a loop. It is not able to coming out from the loop. So we revisit the same scenes or surroundings maps. So identifying when a camera is revisit a previously seen location, using that information to correct drift through the global optimization. That is loop closure. Additionally, the backend manages the map structure, including the maintaining consistency, removing the point, updating networks. It may also incorporate probabilistic frameworks such as factor graph and nonlinear least square optimization methods like Gaussian. In summary, Visual SLAM backend showed that system produces a coherent, drift corrected trajectory and accurate map suitable for long-term autonomous operation. So this is the basic idea. Backend. What are the input to the backend? Backend takes the intermediate result from the front end and performs the global optimization to produce an accurate and consistent map and trajectory. So what are the input? Keyframes, selected frames from the associated pose estimation, initial camera poses, relative or global pose estimation from the front end, 3D landmarks, triangulated map points, feature observation, association between 2D image and 3D landmarks, loop closure constraint, optimal sensor data. What it output? Optimized camera trajectory, the globally consistent poses with reduced drift, refined 3D map, accurate position landmark in the environment, corrected keyframe pose, position and orientation of the all keyframes, loop closure correction, adjustment after the detected revisited location, and covariance answer estimate, the confidence in poses and landmarks. So these are the outputs, and based on this. So here there is some visual sensor, camera, monocular stereo for this. So monocular camera, it is a single camera sensor mounted on the captured video that needs to process and analyze. Scale drifting is the main issue of the monocular camera. Real depth get obtained from the monocular. This is the scale ambiguity. So these are the basic sensors that we are going to use. The stereo camera, it is the system with two cameras separated from the reduce the photometric error. However, the process of finding depth is expensive. It requires depth finding, the calibration, correction, and matching calculation. Now, RGB-D camera, it is also a visual instrument that gives simultaneously depth and color information. Camera can output depth and pixel directly. Hence, it is also called the depth camera. Depth frames have a channel and its grayscale values from 0 to 255. The object is closer to the camera, brighter, and the brightness value is near. Type of camera used in scapulate of the visual. So these are the cameras. Now we try to understand different types of visual SLAM. So visual SLAM, we can say that it is a visual only, it is features based and direct method, and it is a visual inertial, that is loosely coupled, tightly coupled, and RGB-D, that is this RGB camera with depth map and deep learning based. These are the different visual SLAMs. Now in visual only methods, this technique is implemented using 2D images taken from monocular or stereo camera. What is the advantage? The monocular camera based visual SLAM are cost effective, easy to calibrate, and power efficient. The problem with this monocular type has more technical complication due to the restricted visual input, and they are computationally expensive at initialization stage, as minimum 2 views are required for initial depth. So there is a two basic difference in feature based method and direct method. In feature based method, do not use all the information in the frame, rather they use a certain quantity of points of curiosity called key points, and these features are detected from several images. Image matching is done by descriptor. Main drawback is that feature extraction may not be that much fruitful in the texture-less environment. Whereas in the direct method, this direct method state away make use of input images which are free from the abstraction like key point detector or descriptor, nor no pre-processing is of sensor data is required, hence they are called featureless approach. The major drawback is that perform poorly in textureless environment. So these are the basic visual. The visual inertial SLAM or V-SLAMs kind of VI-SLAM kind of or visual inertial SLAM enhance the robustness of the sensor tracking by attaching the inertial measurement in time like gyroscope, accelerometer, etc. Advantage is that they provide additional 6 degree of freedom information like angular rate, acceleration along this axis. The basic disadvantage is that it enhances the information richness of the system. Computational complexity also increases. This is loosely coupled. These are two types of VI-SLAM. As loosely coupled technique execute the IMU data and image data individually and use both data to get the orientation and sensor portrait. Whereas in tightly coupled methods use both the visual data received from the camera and inertial law, that data received from the IMU to improve the precision. So these are some information that we have to remember for this. Now RGB things these RGB-D cameras has depth sensor which allows them to obtain the depth information with reasonable accuracy. The major advantage of this RGB-D advantage is due to this color image data with depth information which decrease the initialization process. But it requires large power consumption, large memory requirement, and it is suitable only for indoor applications. So these are the basic things. What we are mainly interested to deep learning based VSLAM. So supervised and unsupervised approaches are used. Main advantage deep learning is applied to the front end as well as to the back end of the visual SLAM. So it is a lot of improvement on that. And what is the disadvantage? Not much research is done on this obstructive environment occlusion. Next issue is handling real world dynamic environment scenario. So these are some challenges, but there is open research rooms, open room in this research. Now if we see the evolution of VSLAM, it is considered that mono-SLAM is in 2003 and first this was 2006, and this is basically the very early methods, PTAM and mobile phones. So this Kinect fusion kind and real-time onboard VI state estimation. In 2013 there is basically this visual only, this SVO, visual inertial MSCKF, and then SLAM RGB. And there is some. So major thing is coming is deep VO. This is coming the deep learning based. It is 2016. Then comes in SLAM, then deep VO 18, then DF SLAM 19, and DDL SLAM 2020, and deep SLAM, crowd SLAM, and DRYD SLAM, and SDF SLAM. So these are the main deep learning based techniques. Now one thing we just, this is ORB-SLAM, that is important. ORB is a feature oriented monocular SLAM technique. It is a real-time SLAM algorithm and it is applicable in both indoor and outdoor applications. So some characteristics are applied to all activities, tracking, loop closing, and mapping. ORB-SLAM includes the multi-thread tracking and mapping and closed loop detection. The map is optimized using the post graph optimization and binary adjustment. Now what is basically the ORB-SLAM? An open source SLAM system for monocular stereo and RGB-D cameras. ORB is feature matching actually. ORB full from the oriented first rotated brief. So oriented first key point detector plus rotated brief descriptor. So this is the basic idea of the SLAM. Now the thing is that why deep learning is basically advantageous in visual SLAM. So model-based solution, under ideal condition, these sensor and models are capable of accurately estimating systems without time-bound and across different environments. The drawback of model-based solution is that, however, in reality, the imperfect sensor measurement, inaccurate system modeling, complex environmental dynamics, and unrealistic constant impact both the accuracy and reliability of the hand-created system. So that is the major one of the problem. Rely highly on the presence of features and accurate feature matching over different frames. Thus, these methods fail in the case where the environment has very less feature or occlusions. So, when there is occlusion, this kind of model-based approaches is not going to be very suitable. In a scenario with a large number of features, these methods become computationally very expensive and thus limiting their practical use. So, this is also a problem of model-based solution. Now, what is the benefits of deep learning? Why use deep learning? Learning methods can leverage highly expressive deep neural network as the universal approximator and automatically discover the feature in relevant task. That one of the major advantage of deep learning is the automatic feature selection or automatic feature extraction. This property enables learned models to resilience to the circumstances such as featureless areas, dynamic lighting conditions, motion blur, accurate camera calibration, which are challenging to the model by hand. Okay, so the automatic feature extraction is helping a lot in these straight situations. Learning methods allow spatial machine intelligence system to learn from past experience and actively exploit new information. That is also important, that it's past thing we can learn them. By building a generic data-driven model, it avoids human effort on specifying full knowledge about the mathematical and physical rules. So these are the basic advantage of the deep learning based systems. So the learned representation can further support high-level tasks such as path planning and decision making by constructing the task-driven map. So one thing is very important, that support high-level tasks means that is path planning, that in which route the robot will move. So that is very important to understand by basically inspecting the surroundings. The third benefit is capability of fully exploiting the increasing amount of sensor data and computational power that deep learning is handled very easily. Deep learning or deep neural network has the capacity to scale the large-scale problems. The huge amount of parameters inside the DNA framework are automatically optimized by minimizing loss function and by training on large data set. That's the advantage of deep learning. So now we have a high-level conceptual illustration of deep learning based SLAMs. Now here you can say there is a part A, there is odometry estimation, visual odometry, visual inertial odometry, shell odometry, leader odometry. So odometry estimation concerns the calculation of relative change in pose, in translation and rotation into two or more frames of sensor data. It continuously tracks self-motion and is followed by a process to integrate these poses changes with respect to an initial state to derive the global pose in terms of position and orientation. Okay. So deep learning is applied to the model motion of dynamics in an end-to-end fashion or extract useful features to support pre-built system in a hybrid way. So this is the advantage of deep learning over that. Now second is mapping. There is a geometric mapping, the semantic mapping or general mapping. Mapping builds and reconstructs the consistent model to escape the surrounding environment. And deep learning is leveraged as a useful tool to discover scene geometry and semantics from high-dimensional raw data for mapping. Deep learning based methods are subdivided into geometric, semantic, or general mappings, depending on whether the neural network learns to exploit the explicit geometry or semantics of scene, or encode the scene into an implicit neural representation respectively. So basically deep learning is used for different mapping techniques based on these situations. Then comes the global localization. This global localization retrieves the global pose of the mobile agents in a known scene with prior knowledge. This is achieved by matching the inquiry input data with a pre-built 2D or 3D map, other spatial reference or a scene that has visited before. It can be leveraged to reduce the pose drift of a deep reckoning system to solve the kidnapped robot problem. Now, deep learning is used to tackle this tricky data association problem. Okay, that is complicated by the changes in views, illumination, weather, and scene dynamics between the inquiry and data. So these are the advantage of deep learning in different scenario of the odometry estimation, this mapping, and the global localization. In the fourth part is basically the SLAM. This in SLAM integrates odometry estimation, global localization, and mapping process as front ends, and jointly optimize this method to boost the performance in both localization and mapping. So basically, SLAM is doing local optimization and global optimization. These two things. So local optimization ensures the local consistency, camera motion, and scene geometry, where global optimization aims to constrain the drift of global trajectories and in a global scale. So one thing is, you can see that if there is a kind of a local kind of thing when a particular robot in a position, the local surroundings, so how we basically optimize the surroundings. But when we are moving, it is not only the local but several kind such surroundings. So that is a global optimization. So you can say when we basically an image and video kind of the temporal when there is a temporal motion, then we have to use that the inter frame correlation we have to maintain. So in that way, the local optimization, global optimization kind of. So keyframe detection is another that not all the frames. So most of the frames in a very near vicinity is basically redundant. So some frames are very important. So that keyframe detection used by keyframe based SLAM to enable more efficient inference, while system error drifts can be mitigated by global optimization once the loop closure is detected by the loop closure detection. So as we say that loop closure, that we should not just going around in a loop. We should the source and there is a target or source and destination. So we never reach the destination including a loop. So that is done by the loop closure. Uncertainty estimation provides a metric belief in the learned pose and mapping. So this is the whole way this deep learning is basically help to the different aspect of SLAMs. Okay. Now we are going to discuss different deep learning based models for the visual SLAM. You can say 2016 the deep view first come. This algorithm, deep view algorithm, deduce the pose straight away from a series of unprocessed RGB pictures from the videos without embracing any component in the conventional view pipeline. Though through RCNN, it learns the feature representation and implicitly models the sequential dynamics. In deep view, the RNN recurrent neural network estimate the camera pose from feature learned by a convolutional neural network. The CNN architecture proposed is based on the architecture used to compute the optical flow from a sequence of images called the flow method. Then these two stacked along these LSTM layers are applied to estimate the temporal change feature predicted by CNN. So what are the drawbacks? The deep view has no loop closure detection, works in a static environment. That is the deep view. In CNN SLAM, is basically substitute the two major steps, image matching and depth estimation of LST SLAM algorithm with CNN based methods. The algorithm has two major parts. First part applied to the every input frame or camera pose approximated by the reducing the photometric flow between the present image frame and the closest frame. And in second part, CNN predicts the depth of every keyframe. The main drawback is that the CNN SLAM has no loop closure detection and does not work with dynamic. Next is undip view. This undip view is able to estimate the 6 degree of freedom pose of a monocular camera and depth of its view by using a deep neural networks. There are two salient features of this proposed undip view work. One is unsupervised deep learning scheme, and it can estimate the camera trajectory on the absolute scale. Specifically, undip view is trained by using studio image pairs to recover the scale but test it by using the consecutive monocular images. Thus, undip view is a monocular system. The loss function defined the training of the networks is based on the spatial and temporal data. The major drawback of undip view can only be trained on dataset where stereo image pairs are existent. Stereo image recorded simultaneously, and spatial transformation between paired images from stereo cameras are unobservable by IME. Thus, the network architecture undip view cannot be extended to include motion estimate derived from the inertial example. So, these are the basic drawbacks. It also has a drawback that uses the auto-encoder decoder based traditional depth estimator with a tendency to generate overly smooth images. It does not work in dynamic. These are the problems of this. Next, DF-SLAM. DF-SLAM is allowed the ORB-SLAM type framework. However, instead of using the hand-made features, it uses the deep local features descriptor received from the neural network. The main drawback, it does not work in dynamic environment and has loop closure issue. DDL-SLAM attempts to handle the dynamic environment, performance issue, and does not handle loop closure. Deep-SLAM is an unsupervised deep learning based visual SLAM system. The system only requires to do imagery and it does not require any annotating ground truth poses. This concurrently produce the pose estimate depth map, etc. That the major problem with this does not work in dynamic environment has loop closure issue. And SDF-SLAM, the camera pose obtained in the feature point extracted through the CNN works in indoor environment and it also has disadvantages. So in summary, we define the SLAM, simultaneous localization and mapping problem. Then we understand what is visual SLAM and what objective of the visual SLAM. Then the visual SLAM architecture, categorization of visual SLAM. Then we understand that what is the evolution of visual SLAM, what do you mean by ORB-SLAM, and finally conclude by discussing the deep learning based visual SLAM models. The next, we very briefly discuss the self-supervised learning for computer application. Thank you very much.